Welcome to Lecture 3, Advanced Statistical Physics. The subject of this lecture is Bose condensation. So we further consider properties of Bose gases, and it's such a fundamental property of Bose condensation. So this is a brief summary what we'll be doing. I will start with summation rule and introduce maximum population. Then consider phenomenal Bose condensation and its condition. As specific example, I will consider massive bosons in 3 dimensions. I will derive critical temperature for Bose condensation and uncover universal behavior of systems in the presence of Bose condensation. I will finish with thermodynamics of Bose gas in the presence of Bose condensation. We start with the general formula for the number of bosons known to you. So it is similar to what we had for photons and phonons. However, here chemical potential mu is not assumed to be over 0, and it controls the number of particles. So this equation should be considered as equation to find n controlled by mu, or vice versa, to find mu if n is given. The summation over J is the following. J consists of 2 components. First of them is momentum, and second is a spin projection. Because it's massive particle, spin goes from minus s to plus s. Spin is integer by Pauli theorem. Therefore, there is a 2s plus 1 projection of the spin. The summation rule is sum over J of anything is sum over the spin and sum over momentum. Sum of the spin gives this number to s plus 1. It's a volume of the system, and integral over momentum space of the same quantity, but expressed as a function of momentum. Now, I would like you to recall Le Chatelier principle that says if there are 2 sets of variables, x1 and x2 are extensive variables, and conjugated variables are intensive, it's P1 and P2, and this expression of the Le Chatelier principle. So this susceptibility at a fixed extensive quantity is greater than that of intensive quantity. An intensive quantity fixed and greater than 0. Next slide. So I'm repeating the same here. Let us set x1 is equal to n number of particles, and then conjugated variables we know is chemical potential. And x2 will set entropy, and then conjugated quantities as we know temperature. In this case, substituting to this equation, we specifically get derivative of chemical potential over n is greater or equal the derivative of chemical potential over the n at a constant t. The first was at a constant s, and is greater than 0. This part only is interesting for us now, and I will revert this derivative. So if this derivative is positive, then derivative of n over mu, which is inverse quantity, is also positive. That means that n of mu is a monotonically increasing function at T is constant. So at fixed temperature, the number of particles monotonously grows with mu. Or vice versa, mu monotonously grows with number of particles. At the same time, from grand canonical distribution, we know that for bosons, mu cannot be greater than 0. So it's negative or 0. Obviously, the maximum of particles is reached at mu equals 0. So n maximum is n of mu, mu is 0. So this is number of particles, which is maximum, because here is set chemical potential 0. And this is a certain integral that I can calculate if I know dispersion, this function epsilon p, and I know dimensionality of state, dimensionality of the space. Here it is assumed to be 3. But then we'll consider the other dimensionalities. So we'll substitute element of the volume in the momentum space, and we get p squared dp 4 pi. I cancel the denominator, getting 2 pi squared h cubed. This is dispersion of the particle, which at this moment is arbitrary. And I set mu equals 0 to get maximum number of particles. Now let us consider a general case when epsilon p has arbitrary power law. A is arbitrary coefficient and alpha is arbitrary power. Also, I consider space to be d-dimensional. So look here. Here dimensionality is 3. It is sum of 2 and 1. So this index is d minus 1. So I'm writing it in such general form. P to the power d minus 1 dp. Here 2. Now this integral I will not take exactly. I'm only interested whether this integral converges or diverges. Assuming that alpha is positive, which is normally the case, and A is certainly positive, it certainly will converge at large p because this will be exponential cutoff. It only can diverge at small p. So let us examine behavior of this integrand at small p. At small p, the argument of exponential is small. I can expand exponential to be 1 plus argument. 1 is cancels, argument is here, and coefficient A is irrelevant. I don't compute coefficient, I don't carry it. Somewhere here, this is A, element of the solid angle for d-dimensional space. It's always irrelevant. I'm only interested whether this integral converges or diverges at small p. Of course, this integral can be affected analytically. It's simply d minus alpha. It will diverge at small p's when d is less than alpha. So in this case, the system can accommodate any number of particles in the states of the continuum at positive momenta, which is a normal behavior that we would expect, naively. So in such a case, the behavior of the system is regular, and the Bose condensation is absent. Let me repeat this formula. This is also a special case when d is equal alpha. So in this case, that would be dp divided by p. Because this d will cancel this alpha, so it's dp divided by p. It's logarithmically diverges. So and maximum also is infinity, and still Bose condensation is absent. So Bose condensation occurs when this integral converges, and this occurs when d greater than alpha, so dimensionality of the space greater than the index of the dispersion. In such a case, Nmax is finite, so system can accommodate only finite number of particles in the continuum of p greater than 0. If n is less than Nmax, the behavior is completely regular. All particles are accommodated and the Bose condensation is absent. However, what will happen if I add number of particles greater than Nmax? Then we know the states of the continuum with p equals 0 cannot accommodate all these particles, and the maximum they can accommodate is Nmax. And I added more particles, so where the remainder of the particle go? Of course, they go in such a way that the state of the energy of the system is minimized. So they go to the state is lowest energy, and the state is with p equals 0. So the state p equals 0 accommodates all excessive particles over Nmax. In such a way, the number of particles of condensate is, if n is less than Nmax, even equal Nmax, it's 0. But as soon as I exceed Nmax, this excess number is in condensate, and I call condensate number N0. So there are some particle above condensate. And above condensate means at p equal in continuum at p greater than 0. So there is no Bose condensation. If n is less than max, then of course number of particles above the condensate is total number of particles. However, if there is Bose condensation, then above the condensate can be only n max particle. So it's limited. And before I continue, I would stop for several minutes and will let you ask questions. So please, it's a completely new phenomenon for you, and it is a very important phenomenon, both from the point of view of fundamental novelty. You never saw anything like that. And from the point of view of applications. Both condensates have enormous applications in technology, which appeared very recently, but already they are responsible for a significant part of science and technology today. So let me pause, say for 3 minutes, and I would like discussion. Ask whatever you don't understand, and by the way, keep in mind that name condensation is a bit misleading, because normal condensation is formation of droplets in real space. Here, nothing happens in real space. Condensation is in momentum space, obviously reciprocal space. Condensation occurs at p equals 0, when macroscopic number of particles is accumulated. This is this excess over the Nmax. Okay, please ask question. I am waiting. 1 minute left. Okay, let's continue. Most common controlling parameter is temperature. So we'll study now dependence on temperature of the phenomena we're discussing in 3 dimensions and having a standard quadratic or mass type dispersion relation. It's like classical particles, non-relativistic particles. We go back to the equation for the maximum number of particles, which is equation 6, and we obtain, so I substitute at epsilon p, this is epsilon p, p squared over 2m divided by 2kBt. It is in 3-dimensional space, coefficient known to you. And minus 1, of course, is telltale sign of bosons. And you know how we should treat these integrals. There's only one transcendental function. Its argument should be called a new variable. So I introduce variable z, which is p squared of 2m kbt. From this p squared is z multiplied by 2 kbt to m kbt right here. And I will find p from this. It's the square root of it. Now find dp. We'll take dp coefficient index 1/2, power 1/2. Give me coefficient 1/2. So instead of 2 in numerator, I get 2 in denominator. Z has become z to minus power minus 1/2. So it's also denominator. And I'm substituting p squared, this one, and this dp into this equation. So the p squared give me z, and dp give me 1 of square root of z. So I'm left with square root of z. Exponential here is ez and minus 1 in denominator. Power of 2m kbt from this substitution is 1/2 from dp. And first power from p squared, so the 3/2, the power of 3/2. And this coefficient 2 give me 2 to the power of 1/2. So we're done with this. And now this integral is a standard integral. It's nothing else as Riemann zeta function. So I'm repeating it. So this is zeta of 3/2 and coefficient also related to this power, pi power 1/2 over 2. And zeta 3/2 is Riemann, as I told, Riemann zeta function. It cannot be expressed in terms of standard constants, like power of pi, factorials, no. It can be expressed when argument is integer. Here, argument is half integer, so it is not expressible, but you can find it numerically. So if you just take any software, you can easily integrate this expression and get that zeta of 3/2 is 2.61 and change. So this, if I substitute value of this integral, this equation becomes So GV is here, this is zeta of 3/2, and coefficient is pi over 1/2. So it gives me pi to the power, instead of power 2, which is 4/2, I get it 3/2 in denominator, so this pi to the power of 3/2. I put h cubed in denominator as h squared to the power of 3/2 is h cubed, so it is identity. It's substituting zeta function. So what is meaning of n max? As a function of temperature. Let me take given T first. An increased number of bosons from 0 to infinity, then at certain n, which is exactly this n max of T, condensation sets on. And this is given by equation 12. We can formulate this problem in reverse. Let us fix the number of bosons in the system and then decrease temperature. Start with very high temperature, limit infinite, and system is classical, there is no Bose condensate, and go down to the limiting value T equals 0. When I decrease temperature, obviously particles do not occupy states with very high energy. They go down in energy spectrum. Typical energy would be O0 of T, kBT. And of course, because I'm compressing them down, there is not enough phase space for them. And at some temperature, condensation, Bose condensation starts. I will call this temperature critical temperature, T0. At this point, exactly when Bose condensation starts, by definition, n is equal to n max. So there's as many particles a system can regularly accommodate. So n is n max, and I have formula for n max. This is formula, and I only replace temperature by T0. The statement that at T0, n is equal to n max. A definition of T0. T0 is temperature at which Bose condensation starts. Then I can resolve for T0, and I find critical temperature, which would be this coefficient T 2 pi h squared divided by mkb, and then the rest, n divided by this, will be to the power of 2/3. So this is actual temperature phase transition, because both the condensation is nothing else as a second order phase transition. So at this point I also will wait and will answer a question. I have 2 minutes. It's 1 minute. Okay, it's 2 minutes. Let us press. In what follows, we will assume that Bose condensation is present. So I'll set temperature below transition temperature. And again, as I stated, under this condensation, we'll have Bose condensate in this system. I'll show you on several next slides that follow that under these conditions, behavior of the system becomes absolutely universal. I will express it basically in terms of only transition temperature. Okay, so we already know the equation 9, which I cited continuously. This equation for the maximum number of particles, so those particles all accumulated above condensate, that is with p greater than 0. And we will get for it special name n greater, which is above condensate, and it's the same as n max under these conditions. So it is equal to the expression already known to you. I'm just repeating, it's here in these notations. On the other hand, n can also be expressed in terms of transition temperature, T naught, and this is the formula, so temperature T naught, n becomes n maximum in the same equation. And the difference between them is here I can change temperature. Here temperature is fixed. If we give you n, then T naught is defined. Now I'll take these two equations and divide side by side. So I will divide this number of above condensate particles, but total number of particles in the system. Particles are bosons in this case, so it is ratio n greater to n. And the coefficients are absolutely the same. The only difference here is t, here is t naught. So we get c divided by t naught to the power of 3/2. Obviously, our condition is t less than t naught, it should be. So this fraction of above condensate particle is always between 1. 1 is when t is equal to t naught at the Bose condensation. So at the point when Bose condensation just starts, all particles are still above condensate. And when t goes to 0, the above condensate particles simply disappear. This fraction becomes 0. But generally, of course, it should be by definition, it is less than 1. So I repeat this expression. It's absolutely universal as an expression. The power is universal, the dependence is universal. The only thing that will differ different system is the transition temperature T naught. Normalized to T naught is universal expression. Now, of course, I can calculate number of condensate bosons of particle in the condensate. So this excess of number of particles in the system over now number of particles that are accommodated above condensate at positive p. And so this, if I substitute this expression, then greater, this is total number of particles. Again, universal coefficient 1 minus t over t naught to the power of 3/2. When temperature T is equal 0, then n is equal n naught. N naught is equal n. When all particles are on condensate. When I start increasing temperature, that fraction decreases in a universal way, and at T equal T naught becomes 0. Let me again wait 2 minutes. And I will allocate these 2 minutes for you to ask me questions. Please do so. By the way, we agree. Please. One minute. Two minutes. Let's go. Now the concluding part of this lecture is a description of thermodynamics of Bose gas in the presence of the condensate. Again, because we are in the presence of condensate, we must set T temperature less than transition temperature. So let us write expression for internal energy. So this is the summation rule we have. A summation rule is P squared dP. And this is Bose distribution is the same as Bose for number of particles. The difference is an extra coefficient, P squared over 2m, this is energy. It's a familiar expression for energy. Do the same. Do standard change of variables. So this expression, the index, the argument of the exponential, I take as a new variable. So dz is, when differentiate, I get 2p. dp, the same coefficient. And from this I can find p cubed. So I find first p is power 1/2, and then cube it, I get power 3/2. Now I will substitute p cubed and this PdP into this expression. The PdP I will find from this. And I will get, so this is the same coefficient as it was. 1 over 2m is here. From this substitution, I'm getting this coefficient to m kbt to the power 3/2. And then another first power from here. So the total coefficient of 5/2. Z will be in the power cube. Give me z to the power 3/2. And PdP is another, is dz. So it is z to the power 3/2 dz. Argument of exponential is z. So this 1/2 is this 2p. 2 from this 2p. Here the integral evaluates as z to the power of 3 half dz over ez minus 1. It is also zeta function. Argument of zeta function is always this index plus 1. It's zeta of 5 half. The coefficient is expressible in terms of gamma functions. It's elementary, 3 pi to the power 1 half over 4. Zeta function has regular value on order of 1. It is not small, not large. So you can find it numerical. I just took mathematics and integrated at 1.34. We substitute this expression into equation 21, into expression for energy, which is absolutely straightforward. Calculate numerical coefficient and get expression for U. For the internal energy of the system, here repeat expression for N in terms of critical temperature. Then we'll divide them side by side. We'll get U divided by N will be, so I'll take 3 half of this, and 3 half of this will give me T over T naught to the power of 3 half. All these coefficients will cancel, they're the same coefficient. So 2 to the power 5 half and 2 to the power of 3 half is the same coefficient as here, will cancel. I will be left with coefficient 3 half here, and ratio of zeta function. This zeta function or this zeta function. So this 3 comes from this 3, and 2 comes in the denominator is extra 2 because this power of 5 half, not 3 half. We break it into 1 half, 1 in the denominator, and 3 half here. So we got similar universal, similar to the previous, universal behavior. U is equal nkbt. This would have been for classical ideal gas, nkbt. However, here is a coefficient T over T naught, which is less than 1, because T is less than T naught to the power of 3 half. So energy is much less, or significantly less, than temperature of classical gas. So why it is so? Obviously, a macroscopic number, a significant fraction of all particles sits in a condensate at P equals 0, where it doesn't contribute to energy. Let me repeat this formula. Now I can find CV. I will differentiate it over T. And this will give me power of T, which is 5 half. The coefficient will have 5 half. U divided by T, differentiation removes 1 power of T. Well, this 5 half by 3 half give me 15 over 4, ratio of zetas, and power of 3 half, temperature is left. Now I will find entropy. So this expression already known to you. So it comes from CV is equal T ds over dt. Divide by T and integrate, I get S. And coefficient is restored by Nernst theorem. At T equals 0, S must be equal 0. So this is this integral from 0 to T. We already discussed it. So I integrate power of 3 half. I'm getting power of 2/3. So it was power of 3/2. I decrease it by 1, integrate. I'm getting back power of 3/2. So coefficient is inverse power 2/3 CV. And this CV is 5/2 u divided by t multiplied by 2/3, 5/3 u divided by t. Next slide. Now I find Helmholtz free energy, u minus ts. So u minus, this is s, 5/3 u divided by t. T cancels and give me minus 2/3 u. Now I substitute u from the expression that we found it initially. I just repeat it here. So we multiply it by minus 2/3. So coefficient will be minus 2. This is expression for Helmholtz free energy in terms of the volume and temperature. And because we are below the condensation temperature, the total number of particles is irrelevant. Because when you change total number of particles, excess goes to condensate. And those particles that contribute above condensate is a constant, is n max. It's a very interesting fundamental property. You never will find n in here. But it's irrelevant. N doesn't control anything, it just controls number in condensate. And condensate doesn't contribute to thermodynamics. Finally, we can find pressure. This derivative of F over V simply removes this V. It at constant C, so this T is constant, at constant N, but again explain you, N never enters this expression below the condensation temperature, because N doesn't control anything except for number in condensate, but number of condensate is irrelevant for thermodynamics. It doesn't contribute. It has zero entropy, zero energy, everything is zero. So we just remove V, change the sign, and this expression for pressure. So for ideal gas, classical gas, pressure is simply kBT. Here it is much stronger, depends on temperature. It's not first power of temperature. It's 5/2. So why such strong dependence? Very simple. When you increase temperature, not only particles above condensate acquire more energy and increase their pressure, more particles come from the condensate. And therefore this dependence stronger than T to the first power. So this is due to the presence of the condensate. Now this is the bonus material. This is brief history of the discovery, very brief. So the Nobel Prize was given in 2001, awarded to Eric Carnell, Wolfgang Ketterle, Carl Wieman. Carnell and Wieman are from University of Colorado, Boulder, and Carnell from MIT, for achievement of Bose-Einstein condensation diluted gases of alkali atoms, if an early fundamental study of the property of the condensate. This is exactly what we've been presenting in this lecture. So how does the main result of the groundbreaking experiment looks? This is the graphics. So this is two-dimensional distribution. It is px, py, and vertical is the number of atoms. Overall, a few thousand atoms was in a trap. Experiment is done this way. They are kept in a trap and cooled down. And then velocity distribution are measured by releasing them from trap and looking how the atoms fly away. Gives you a pretty good idea of number of atoms flying in every direction with a given velocity. The observation was by fluorescence of bright lines of alkalis. They have very characteristic lines. Sodium is very bright yellow lines. This is pictured just before onset of the condensate. So atoms were cooled and the velocity measured, cooled and measured. So this is very smooth distribution. It's a typical, almost Maxwell distribution at this moment. Almost classical gas. So then trap was slightly open and atoms were allowed to evaporate. It was phenomenon, you know, it's evaporative cooling. The hottest atom fly away, coldest atom remain. Overall temperature goes down, the number of particles goes down. At this moment, measurements of the velocity distribution shows a singularity at zero momentum. This is the Bose condensate. Surrounded by a cloud of the above condensate atoms, that's what we have. And then this cooling continues. Basically, it was pretty rapid cooling. The trap was almost completely open. So the overcondensate atom flew away, temperature went down. And in this case, we have almost 100% in the condensate, almost zero above condensate. So it's basically illustration to what we have studied. So let me wait a minute until you ask questions regarding this experiment, if you have one. Otherwise, we came to the end of the lecture. I'll wait 1 minute. And then after lecture is over, we have technically unlimited time to ask, but of course, everybody is busy. Okay, time is over. Slide and the lecture is over. Now, as I finish this lecture, slideshow will end and we'll have ample time to ask questions.